In the previous lecture, we saw that the class of the hyperplane generates the cohomology of CPN. In this lecture, let us use this to compute the cohomology of P of E over M, where E to M is a complex vector bundle. So first, let's see how to construct P of E given a linear map. An isomorphism. It induces a map on lines. Thus, it induces a smooth map. PNC to itself. In particular, we can use this to glue UI times PNC using the same transition functions psi ij from uij to glnc, which were used to construct D. Thus, P of E is a locally trivial fiber bundle over M with fiber over X being P of E sub X. So our aim is to prove the following result. There is a class theta in H2 of P of E such that the restriction of theta to each fiber is the class of the hyperplane in P of E sub x. So let pi from P of E to M denote the bundle map. Then there is a line bundle which we denote O PE minus 1 on P of E, which sits in a short exact sequence of bundles on P of E. So the sub bundle O PE minus 1 is constructed using the gluing construction for simplicity of notation. We denote it by L. By construction, for each point P in P of E, the line LP is going to be contained inside pi upper star E sub P, the fiber of pi star P, which is equal to E restricted to pi of P. And this line will correspond to the line given by P in the fiber E restricted to pi. And moreover, Q is simply a quotient. Because L is actually a sub-bundle. So over each fiber, it's an inclusion. So this is something which we have seen before, that if you have an inclusion of bundles, then the quotient is also a bundle. So let X be a compact smooth manifold and let L be a complex line bundle on X. We can find finitely many global sections of L dual which generated everywhere. That is, equivalently, we can find a surjective map of bundles. From the trivial bundle X cross C plus 1 to L dual. And taking dual, this is equivalent to saying that we can find an inclusion of bundles X cross C n plus 1. For each point P, P in X, we get a line L sub P sitting inside Cn plus 1, and this gives a pointwise map from X to Pn. So it is easily checked that this map is smooth. And in any case, we will come to a precise, we'll see a precise definition of this later. So pulling back, the class of the hyperplane we get a class in H2XR. This class is denoted C1 of L. Let us show that this class is independent of the choices of the global section. Now suppose we have two inclusions. Phi 1 to Cn1 plus 1 and Phi 2 to Cn2 plus 1. Okay, this should be X cross then we get two maps. F1 and F2. So let n be equal to n1 plus n2 plus 2. Embed Pn1 Pn as the first n plus 1 homogeneous coordinates, and Pn2 into Pn as the last n2 plus 1 homogeneous coordinates. It is clear that these are embedded as linear subspaces. So denote theta n to be the class of the hyperplane in Pn. Then it is clear that I1 upper star theta n is theta n1 and I2 upper star theta n is theta n2. Since we can find a hyperplane which meets the image transversely, thus it suffices to show that f upper star f1 upper star I1 upper star theta n is equal to theta n. So we will show that the two maps G equal to I1 compose F1 and H equal to I2 compose F2 are homotopic. So let us recall how the maps F, H and G, G and H are defined. So let UI be an open cover for X over which L is trivial. So then we have a non-vanishing section SI so Thus, consider the map is phi 1. So, by abuse of notation, we will view this as a map from C. You have to see n plus 1. Thus, the map G on UI is given by x goes to phi 1 compose Si and then zeros in the remaining coordinates is 2 plus 1 coordinates. And similarly, the map H on UI is given by x goes to so consider the map f lambda I from UI to Pn given by lambda times phi 1 composes I colon 1 minus lambda times phi 2 composes I. So notice that it cannot happen that all the coordinates are 0 for any lambda. So lambda is in complex numbers. And let us check that f lambda I is equal to f lambda j on UI intersection uj. So the sections Si and Sj satisfy Sjx is equal to psi ij x Six, where psi ij's are smooth maps from uij to C star. Thus, f lambda j x is lambda phi 1 compose sj colon 1 minus lambda phi 2 compose sj. This is equal to lambda into psi ij of x phi 1 compose si colon 1 minus lambda psi ij of x into phi 2 compose si. That's because phi i's are linear on the fibers, and this is equal to f lambda I of x. Thus, f lambda glue together to give a map x to Pn. It is clear, or can be easily checked, that is a smooth map. This proves that G and H are homotopic. Thus, C1L is well defined. So in particular, we may apply the above discussion to P of E. And the line bundle O P of E minus 1 on P of E. Thus, we get a class theta h2 P of E comma R, and when we restrict theta to a fiber, PEX, then it is clear that we get the class of OPE minus 1 restricted to P, the fiber, which is exactly equal to OPE fiber minus 1. However, on Pn, the tautological sequence, so this is OPn, this Pn if rank of E is n plus 1, gives rise to the identity map. from Pn to Pn. Thus, the restriction so I should write C1 of this thing is equal to C1 of this thing. Thus the restriction theta set to Pe of x is the class of the hyperplane. In Pex, and this happens for all x in the base m. In particular, this proves that the restriction of the classes 1 theta up to theta n, these are global classes, to form a basis for the cohomology of the fiber. Thus, the Leray-Hurst theorem applies. So theorem let pi from B to M be a fiber bundle. With fiber F. Suppose there are cohomology classes E1 up to ER such that the restriction for each x in M, the restriction EI restricted to P sub x, the fiber, forms a basis for H star P sub x. Then the canonical map is an isomorphism. So the proof of this, when M has a finite good cover, is similar to the proof of the Corinth formula. and is left to the reader. Let's now define Poincare polynomials. Suppose we have a manifold with finite dimensional cohomology, then we define its Poincare polynomial P&T to be equal to T to the power I. From what we have proved, it follows that for a complex vector bundle, of rank n plus 1, the Poincare polynomial of PE is in fact the Poincare polynomial of any fiber bundle in the situation, okay, let me not make this remark, but let me just say it, that in the situation of the Leray-Hirsch theorem, we proved that the Poincare polynomial is, our total space is just the Poincare polynomial of the base and the Poincare polynomial times the Poincare polynomial of the fiber. And let us make one last remark, that C1L is defined even when X is not compact. Although we have defined it here only in the case X is compact. So we'll stop here.